All right, so these are the notes that I was talking to you about. It's basically a continuation of improper integrals. So take a minute and definitely read this top portion. But basically, if you remember, improper integrals are the newest thing that we're looking at in terms of integrating. And now that improper integrals are in play, you have to basically always look for the fact that an integral could possibly be improper. You can't always assume now that they are all going to be proper or they're all going to be improper. It could be either or. Now, if it's improper, they're evaluated by rewriting the integral as a proper integral and using the limits. But how do we rewrite them? There are different things, different ways that we've learned on how to rewrite an improper integral as proper. So, when determining if an integral converges or diverges, the following information can be helpful. So what we used to do before is we used to look at this problem and kind of combine, get a common denominator, and then go from there. These little rules kind of help us out a little bit. And if you notice that anytime you have, if one of the two functions is divergent, then the whole function is actually going to be divergent. And that's if you're adding. So even if the other part is convergent, if one of them is divergent, then the whole thing is going to be divergent. And if one of them is convergent, then you will have to check the other one, because a convergent plus a convergent will give you a convergent answer. Now this right here tells us that a divergent minus a divergent is going to give us an indeterminate form, and if you remember, if you get an indeterminate form, you can use L'Hopital's rule. So all this is just a little shortcut. So instead of us having to combine like terms here and then go from there for this improper integral, this infinite improper integral, what we can do is basically separate this integral into two. So then we'd have, I'm going to treat this like a free response. So we would have the limit as b approaches infinity of the integral 1 to b of 1 over x plus the the limit, okay, I'm going to put that in parentheses, 1 to b of 5 over 1 plus 5x, and they're both of course dx. Okay, and again, I'm sorry I didn't give you guys a lot of space on these notes, but this one is a Word document, so you can actually space this out a little bit. So this is an easy integral to figure out. So the integral of 1 over x just becomes, so the limit as b approaches infinity of ln of the absolute value of x plus, now what is the integral of this? We're going to do a little side work. How would we integrate that? Now just by looking at this, I see that the derivative of the bottom portion is actually in the top, so I'm going to use u substitution. So if I let u equal 1 plus 5x, then du is going to be 5. 5 dx. Okay, and now if I rewrite this, this becomes the integral of 1 to b of 1, or du, I should say, over 1 plus 5x, or sorry, the du over u. And so the derivative of this becomes ln of, or the integral becomes ln of u. And here ln of u is going to be 1 plus 5x. So this becomes ln of, and this of course is ln of the absolute value of 1 plus 5x. And then this whole thing is integrated from b to 1. So we can continue this by plugging in b into and 1 into each of these terms. And we know that this, once we plug in our b, let me just write the next part right here. So limit as b goes to infinity of ln of b minus ln of 1, and we know that ln of 1 is 0, so I'm not going to write that down. So minus the second part, which is ln of 1 plus 5b, and then ln of 1 plus 5 times 1, which is ln of 6, so minus ln of 6. And here's the idea. Basically, we know that ln of b is infinite. If you plugged in infinity here, so ln of infinity is infinity, minus ln of 1 plus 5b, which is another infinity, is infinity. And then, of course, this is going to be just plus ln of 6, so it doesn't really do anything with infinity. So based on our little information, divergent minus divergent, so infinity minus infinity, means that this thing is an indeterminate form. And what do we do with indeterminate forms? We have to set it up as a L'Hopital and solve that. So this is indeterminate. So I'm going to have to combine these somehow to be an f of x over g of x and figure out what my actual answer is. Okay, I'm just going to turn to the back side and show you guys how we're going to do that. So the limit as b goes to infinity of ln of b minus ln of 1 plus 5b plus ln of 6. And the reason it became plus is because I distributed that negative. Okay? And now what we can do is basically combine these two guys using the log division rules. So this becomes ln of b over 1 plus 5b plus ln of 6. Now I can use L'Hopital's rule because this is my indeterminate form, infinity over infinity. So find the derivative. So this becomes ln of 1 over 5. Don't forget the ln of 6. So now my final answer is going to be ln of 1/5 times 6, which is ln of 6/5. So that's what that little shortcut helps us figure out. Okay, if you end up with the infinity minus infinity, you know it's indeterminate. It just kind of gives you a little heads up of how you're going to continue solving this problem. All right, part 2 is a little bit easier. So let's set this up as the limit as b approaches infinity of the integral from 1 to b of 1 over 2x minus 1 dx. How do we integrate this? We're going to have to use u substitution. I'm not really going to show you how to do that. You guys can do this on the side. But here we end up with the limit as b approaches infinity of 1/2 ln of the absolute value of 2x minus 1 from b to 1. Plug in your b and your 1, and you get the limit as b approaches infinity of 1/2 ln of 2b minus 1 And then here, if you plugged in 1, of course you would get 0, so I'm not going to write that down. Minus 1/2 ln of 1. Actually, we'll write it down, but we know that ln of 1 is going to give us 0, and we'll talk about this in just a second. So here, now if I was to plug in my limit, what do I get? I get ln of infinity minus ln of 0. So anytime you have one portion that diverges, and the second portion was not a divergent, okay, it was specifically convergent. So guess what my answer is? I don't even need to continue solving this. I know that it diverges and diverges to infinity. Alright, improper integrals where both bounds are infinite. So this looks like harder than it truly is. Let's evaluate the following integral. You guys can take a second to read this, but you can see what we're going to kind of do. Okay? We're going to break it up into two separate integrals. And C, how do we find C? It can be any value, but 0 is often the easiest choice. Okay? So let's put a little note here. So C can be any value, but 0 is often easiest. So I'm going to be using 0 all the time. Now every once in a while, if you notice that, using 1 will cancel something out, you probably want to use that. So I'm going to set this up, and then you guys can finish this off. So this is obviously improper. We can't take from negative infinity to infinity, so we have to break up this integral into two parts. And the first part is going to be from negative infinity to 0 of 1 over 1 plus x squared dx. And then the second part, we're going to add, because we have to get to infinity, is from 0 to infinity of 1 over 1 plus x squared dx. And now you're just going to treat these two individually. So the first part is going to be the limit as b approaches negative infinity. Sorry, that's supposed to be a negative. Okay, so my screen went black, but I'm assuming you guys are still seeing what I should be seeing, so I'm going to continue. Alright, so the limit as b approaches negative infinity. And actually we may want to change from b's to b's and a's. So if this first part, let's make it a to negative infinity of a to 0 of 1 over 1 plus x squared dx, plus the limit as b approaches infinity here of 0 to b of 1 over 1 plus x squared dx. And now you're going to integrate and then plug in your negative infinity and your infinity. So I'm just going to tell you that your final answer is going to be pi for this one, because if you guys noticed, what is the integral of 1 over 1 plus x squared? It's going to be an easy one. It's inverse tangent. Or it would be easy if you remembered it. Alright, next example. Same. You're just going to break this up into negative infinity to 0 of x e to the negative x squared dx, plus 0 to infinity of x e to the negative x squared dx. Use the limit definition. So we set this up and integrate it. I hope you guys noticed how to integrate this. So it's the limit as b approaches gosh, I'm gonna do this a lot. Negative infinity of a to 0 of x e to the negative x squared dx plus the limit as b approaches infinity of x e to the negative x squared dx. So I hope you guys notice how to integrate this. So this next part for integration, what are we going to use? You notice that this part right here is negative x squared, so therefore du could be negative 2x, which is right here, just with a constant coefficient, so we can get rid of that coefficient and that minus by dividing both sides by negative 2. So x dx can now be replaced by negative 1/2 du. Alright, and I'll let you guys finish this off just because I don't want this video to be super long, but your final answer will end up being 0. Alright, find the area of the region bounded by the graph of y equals 20 over x squared plus 1 and the y-axis. So if we graph this, focusing on the x-axis, 20 over x squared plus 1. So basically when x is 0, our y is 20. When x is 1 or negative 1, our y is 10 and 10. When x is 2, so 2 squared, so 20 divided by 5, our y is 4. And when it's negative 2, it's 4, and then when it's positive 2, it's 4. And it gets closer and closer and closer, but it truly never touches the x-axis. So this is our graph. Okay, and you can test it out. When x is negative 100, you're going to get 20 over a very big number, which is a very small y. So we want to find the area of the graph with the x-axis. I really hope you guys are seeing this because I'm still taping and I can't see my screen. But I will stop here after this problem. So we are finding the area from negative infinity to infinity, because on both sides this is never truly touching, of this function 20 over x squared plus 1 dx. So you're going to be using the bounds. So we're going to separate this area basically into two parts. We're going to find from negative infinity to 0 and then from 0 to infinity. So I'm going to just right away write it with a to negative infinity, from negative infinity to a of 20 over x squared plus 1 plus limit as b, because it's a separate area, infinity of the integral sorry guys, this is supposed to be 0, this is supposed to be a, and then here we're going to have 0 to b of 20 over x squared plus 1 dx. So integrate this. I hope you guys notice that you can pull out the 20. And again, you're left with the same exact problem as this. 1 over 1 plus x squared, which is the inverse tangent. And then you can plug in your b, and you should get an answer of approximately 20 pi. So I will let you guys complete this, and hopefully you were seeing what I was drawing, because I can't. Alright. I'm going to make a part 2 video for the rest of these notes.